Welcome, everyone. Welcome to this week's K-Core Zoom presentation, number 183 to be exact. Our speaker today is Raymond Leury. He's spoken to us on several occasions. He has a special interest in science and environmental issues, and a special interest in electrically powered vehicles. In fact, he is president of the Electrical Vehicle Council of Ottawa. In January, he spoke to us on the need to adopt technological change currently available in energy systems if we are to be able to select pathways which will enable us to limit global warming to around 2 degrees centigrade. He believes this is possible. Today, he will continue on this theme, calling this part 2, expanding to implications for other parts of the economy. So I welcome Raymond and hand the floor to you.
Thanks very much, Nigel. Just one small clarification. I'm not sure if we could keep to 2 degrees Celsius, but that's another matter which I won't discuss today. What I'm going to do today is I'm going to go over some of the stuff we went over last time to remind you of some of the things, but mostly I want to talk about things that weren't covered at the last presentation. So again, my as I described, my superpower is that I've always worked in the intersection of business and science or technology, and for the last 20 years or so, my task was to figure out how to get the thing done, no matter what people said was possible or not. Right. So when you're faced with that, you start to think about if someone tells you no, you start thinking about why or how you can make it a yes. Anyways, never say never. I said this last time, and the point here is that what was false in the past may be true today. Okay, so and I use the example there with a smartphone that in 1990 it was impossible for us to do what we could do with a smartphone today. Now the interesting thing there is that if you know something about Moore's law, Moore's law actually forecasts that this would be possible at some point around the year 2000. So actually a bit after that. So there are other things like that we could forecast, okay? So the point here is if you looked at some technology or subject matter that has to do with technology, it might have changed since the last time that you looked at it. So the laws of nature don't change, but the technology evolves, and there are things that we could do now that we couldn't do before, okay? So one example that I've heard a lot is we can't make windmills without fossil fuels. I won't cover in detail windmills here, but I hope to explain to you that this is in fact false. We can make windmills without fossil fuels. So hold my beer, and we're going to go over how we could do that. But so let's go to the next slide here. So what did we get from part 1? There's a lot of greenwashing, especially in the technology area, and different solutions that different proponents are proposing to address this climate change issue. And let me just put that. So the IEA, as I had discussed last time, they woefully understate the pace of change. So we're seeing that specifically with solar, wind, batteries, and EVs, and the adoption rate of those technologies. So they're actually being adopted much, much faster than what the IEA is forecasting. And one other thing I want to point out is that there's an organization called Decarb Connect that I've attended some of their conferences, and they talk about a lot of the things that I'm going to go through today. They're industry associations essentially that are looking for ways to decarbonize their particular industry, and they're trying to share the information to accelerate the decarbonization. Right. So they're based in Europe, but they also do some work in North America and other parts of the world. So fossil fuel incumbents, we covered this to some degree before. The writing's on the wall. They know that things can't continue the way they are. Otherwise, we're going to fry the planet literally. But they're trying to hold on to the market. They're using all means that they could possibly have to slow the transition. We were talking about this a bit. earlier on with misinformation before we started the recording. Today, it's hard to tell what is the truth. Okay, and I'll use a very simple example here. There was a lot of press about the EV sales softening. Well, if you look at the real numbers behind this, there was indeed a bit of a slowdown in the US in the fall. However, if you look at the dynamics behind that, the IRA, Inflation Reduction Act, the US was actually deciding on what the rules would be for 2024. And if you were if you're an American intending to buy a Tesla or a GM product or a Ford product, you were probably much better to wait until January 1st to do that. So there's some people who decided to postpone the purchase. There are other examples where the opposite applies. So Hyundai actually sold 3 times more EVs in November 2023 than they did in November 2022. Okay, 3 times more. So that's not a softening in my book. And actually, the only place where we saw something that might have looked like a softening is in the U.S. Everywhere else, we're not seeing this. So think about the cigarette companies and what they've done over the years. Actually, the same PR firms that we're talking and working with cigarette companies back then are working with the fossil fuel industry to try to misinform people. And of course, they're trying to protect their interests, right? So this is one of my favorite quotes. It's from Warren Buffett. And his quote is, "Never ask a barber if you need a haircut." The idea there is that there are many cases where, if people want to know something about the auto industry, they'll go and talk to the auto manufacturers. Well, the auto manufacturers know a lot about their business, but they're not necessarily going to tell you what you want to know. They're going to tell you what they want you to know. So if you look at the EV sector again, you'll see some companies pushing back for reasons that are of their interest and not necessarily telling you the truth. Okay, so I could go through a lot of examples of that, but there are many examples where people, because they have a vested interest in a particular technology or market or whatever it is, they're going to make arguments that are in their favor, obviously. So in terms of pace of change here, just briefly, so the IEA, again, the forecasts, they're usually linear. They should be S-curve. This is an example of some of the things that, some of the technologies that have been adopted over the last century or so. You see around 1945 a dip for a few of them, clothes washers and autos. That was because of the Second World War, and actually part of it was because of the Depression, right? So if you look at the Ukraine war, it had an impact on a lot of things because it's a shock to the system, right? But generally speaking, what happens over time is we're following an S-curve, slow adoption at first, ramps up really fast, and then it peters off over time, right? So that's what we're seeing with all the technologies that are out there. And the IEA doesn't seem to have figured that out yet. So that's it's a concern for me, particularly because you have governments that are relying on the IEA's forecast to make policy decisions. So how fast can this be? This is an example with Norway and their EV adoption. So in January of this year, 94% of cars sold in Norway were electric. So, and just a very small percentage, less than 2%, was plug-in hybrid. So they're almost all purely battery electric. Okay, so this happened in Norway for a bunch of reasons. I won't go through all the details there, but you have to think about this happening in a context where for most of that period, there weren't very many choices available on the market. There were other impediments to making that happen, but it still happened. And if it followed more or less an S-curve, right? Now I want to talk about something. Last time I talked about CCUS, carbon capture, utilization, and storage, in the context of greenwashing. And I want to talk this time about hydrogen in that context. And this is partly in response to a question I got from Dave a little while back about hydrogen and hydrogen vehicles. So hydrogen has been proposed to solve just about any problem that's out there, right? So you may have heard this, that we could use hydrogen for planes and for trains and for buses and all this stuff, light duty vehicles, et cetera, et cetera. So it seems that for some reason, when there is a problem to solve that has to do in some way, shape, or form with energy, in this case, it's mostly energy, that hydrogen becomes the solution. Okay, so the problem with hydrogen is it's like this humongous Swiss Army knife, and apparently this is a real one. That and actually sell for $1,500 US. It does the job for all of these uses, but it's not particularly good at the vast majority of them, and we'll go through that to explain how that works. So hydrogen works just like carbon capture and sequestration. That works. You know, you can't say that it doesn't. Same with hydrogen. We know that fuel cells work. We know that there's a bunch of other things you could do with hydrogen that actually work. Technically, you could make it work, but is it a good solution? Okay, so this is where it falls short. So if you look at the example of cars here, the first column is a pure battery electric vehicle, and if you look at the bottom, that's the efficiency from essentially from what would be the equivalent in a gas vehicle of well to wheels. Okay, so the overall efficiency from everything that's used to provide energy to propel the car. So if you look at the overall efficiency, they say 77%. That's, you know, ballpark. If you remove the some of the downstream stuff, and most comparisons that are done here, by the way, they will look at the full well to wheel energy requirements for EVs, but they won't do the same thing with ICE vehicles. So what they tend to do there is they look at the tank to wheel efficiency. Okay, and we'll talk about that a bit more later. But so with a battery electric vehicle, we get 77% or so efficiency. With a hydrogen fuel cell vehicle, because we get losses along the way, we get about 30% efficiency. And what I would say is this: 30% is optimistic. Okay, if you look at this last column, that's power to liquid. Excuse me. What power to liquid is, you would do you use electrolysis to produce hydrogen. Then you would use some carbon capture of some sort, probably direct air capture here, and use those. So use the CO2 and the hydrogen to produce synthetic fuel. Okay, so if you look at that at the bottom there, 70%, that's the that reflects the inefficiency of an internal combustion engine, because here the liquid would be use in an internal combustion engine to produce power, right? So 70% is quite generous, actually. In many cases, you lose more than that. So you can see there that there's a huge difference in efficiency of all these. Hydrogen in particular, compared to a battery electric car, we're talking somewhere around 3 times more energy that's required to essentially get the same distance. So you could either, you know, use 1 kilowatt of electricity to get, you know, a certain amount of distance with an EV, or you do the hydrolysis and fuel cell and all that stuff, and you get 1/3 of the way with the same power, right? So that's a bit of an issue. So here, what I'm showing is that, what I'm saying is hydrogen's got a more or less 3 times energy penalty. So it's a huge cost disadvantage. Okay, energy is never free. It might become cheaper in the future, but it will never be free. So this imposes a penalty to start off with on hydrogen. If you look at how can you explain that, it's really about the laws of nature that get in the way here. You look at the graph on the right-hand side, you would start, let's say, with water at the bottom left-hand side, that red curve we see there. You would apply some mechanism, which in this case would be electricity through hydrolysis, and then you'd get the hydrogen, which would be at a different level of energy. Okay, so you would be storing some of that energy into the hydrogen, but in the process you lose lots of heat because that's just the way the physics and chemistry works, right? So every step of the way, if you're transforming something into something else, you lose some energy. Same thing here, going backwards in the fuel cell, you lose some energy going from the hydrogen and combining it with oxygen to go back to water and produce electricity. Okay. So if you look at so lots of energy is wasted as heat. Internal combustion engines, again, 70%, 80%. This is tank to wheel, not. If you consider the energy required to produce the and transport the fuel, it's quite a bit less than that actually. The other thing with with hydrogen is that you need to store it somehow. So if you're storing it under pressure, you're talking about 5,000 to 6,000 to 10,000 psi. And a reminder that at the where the Titanic is right now in the water, the pressure is 6,000 psi. Okay, on the low range of what you would need to be able to store hydrogen in your vehicle or wherever else you're storing it if you're using pressure to get more density. The other option is to refrigerate it down to about 23 Kelvin, which is hard to do and it takes lots of energy. So bottom line there, the storage is costs you a lot of energy because of this need to either compress or refrigerate. So you may say, well, Raymond, what if I convert it into ammonia instead? And then I don't need to refrigerate as much or compress as much, right? So yes, that's possible. But if you look at that and you look at the graph on the right-hand side, so converting the hydrogen to ammonia would be like going from the first yellow square to the next yellow square. And so there's a loss of energy there. So every step, there's a loss of energy through the process that generates heat that you can't recover, all this kind of stuff, right? So there's nothing really, there's no free lunch, is what I like to say, right? So a lot of people have proposed using ammonia instead of hydrogen because it's somewhat easier to handle. I'll remind you though that hydrogen is explosive, but ammonia is extremely toxic. But anyways, I'll leave that aside for now. So we have a disadvantage in terms of the production of energy, huge disadvantage. We also have an issue with the kit required to do hydrogen. So if you look at the left-hand side, that's the electricity going to a battery in an electric car. So the car on the right is essentially the same car as on the left, except it's got a smaller battery, but it's got additional kit that you require for the hydrogen. That's the fuel cell, that's the tanks, and the tanks, by the way, could be quite heavy because of this pressure requirement, right? If you look at the rest of it there, you need electrolyzers. You need to, if you're trucking it, because of the volumetric density of the hydrogen, you would need 6 trucks of hydrogen to replace 1 truck of gas or diesel. Okay, so you need lots more trucks, lots more energy to move those trucks, et cetera, right? So that makes it even more expensive to do hydrogen. So essentially, that's really the case for why hydrogen is not a good solution for transportation applications and for energy applications. So electric solutions are more efficient than hydrogen, more efficient than fossil fuels actually also. So again, transportation 3 times better with electric than hydrogen. Heating, if you're burning hydrogen, so there's been proposals to add hydrogen to the natural gas system and get some of the energy that way for heating and cooking. Well, if you look at that and you run the numbers, the amount of energy required to do the electrolysis, if you put it into an air source heat pump instead, you're going to get 6 times more heat. Okay, so huge performance penalty there. And heat pumps, they work to 200 degrees Celsius. And if you talk to Art, he'll tell you that with ground source heat pumps, you get even better efficiency. So bottom line is it's not a good solution for transport energy applications. Excuse me. There's other issues that I haven't talked about. Safety in particular, I haven't talked about. But hydrogen has other uses, and we'll get to that later when we talk about some of the other stuff that's happening out there. There are 3 references there that are quite interesting. If you want to learn more about this and some of the background information on this, Professor Simon from Cambridge has got a great video that goes over that in a very approachable way. Michael Liebrich, who's the guy who founded what became Bloomberg NEF, New Energy Finance, he talked to the World Hydrogen Conference in our Congress in 2022 and essentially told them what I'm saying here. Okay. So it's interesting to see what he has to say, and I'll talk about some of the things he said a bit later on. Paul Martin, we'll have Paul Martin actually as a speaker in June. I've invited him to come over and talk to us, and he's the one who came up with that Swiss Army knife comparison. So a bit more about hydrogen, not, and I'll try to make this fast because there is a lot of other stuff I want to cover. If you look at the possible uses of hydrogen, this is Michael Liebrich's hydrogen ladder. At the top where it's green, those are areas or industries or solutions where hydrogen is really the best solution out there. Okay, so if you look at fertilizer, right now the fossil fuel industry uses methane to produce hydrogen to then do ammonia for fertilizers. Okay, so we need hydrogen for that. We need it for a bunch of other purposes. Steel is not quite at the top, and you'll see why later when we talk about steel. But we could use hydrogen to make steel and chemical feedstock also. So without going into too much details here, really the best uses for hydrogen have to do with the chemistry of hydrogen, not the energy content that you could get in hydrogen. Okay, so lots of information on there if you look it up. I got a link there that gives you a lot of information. Last thing about the the hydrogen picture. So this is a comparison on the left-hand side of battery electric sales, and that on the right-hand side, that's fuel cell vehicles sales. And it might look like there's nothing on the fuel cell side, but no, it's so small that you can't see it. Okay, so the the hydrogen industry might tell you that sales are booming, but they're still very, very low. And actually, they're being the sales are to fleets and projects where they're trying to figure out how to make hydrogen work for their own purposes. So there's lots of greenwashing happening here. Okay, it's not, again, that it doesn't work, but it's not the best solution for most applications. Now you have to think about what if there's greenwashing, why is there greenwashing? Well, who benefits from hydrogen? Okay, a little clue here, follow the money, right? The money is usually a way to figure this out. So green hydrogen, so hydrogen from electrolysis, is somewhere around 4 times more expensive than what are referred to as gray hydrogen, which is from methane. So the fossil fuel industry knows this, and they're probably thinking, hey, I could sell some of this gray hydrogen. Meanwhile, because when push comes to shove and budgets get tight, people choose the cheapest solution, right? When it's available to them. So the fossil fuel industry, by the way, produces about 120 million tons a year of hydrogen. Okay, that's feedstock for some of the stuff we talked about in the ladder before. That results in about 700 million tons of GHG equivalent emissions per year. Okay, lots of emissions. So if we could get rid of that, it'd be great. So what we should be doing with green hydrogen, which is, we expect that green hydrogen is going to become cheaper over time. But what we should do there is we should replace the existing hydrogen that we produce before we look at doing anything else. So yes, there are other uses. We'll talk about some of them later, but really we should be focusing on replacing what we have right now. So last presentation, I had this here. What are the choices? I had 3 options, and essentially what I was saying is the option that I think is the only option, I'll just go through here and show it all, is option 3, where we need to find some way to decarbonize. I mean, there's other things, I won't go into all the details, there's other issues we need to address aside from climate change. But bottom line, from a climate change perspective, we need to decarbonize our civilization as fast as possible. And that's really, I believe, the only solution that will actually be accepted by most people. Because if you're saying, well, we're going to go back to some less technologically dependent civilization, well, we probably can't support very many people. I'm saying here maybe 1 billion or so that you could support with that. Well, that means that we would have to sacrifice or ask 7 billion people to vote themselves off the island, and they won't do that. Okay, so to me, it's the only acceptable solution. So when we're looking at implementing it, we want to avoid bad stuff, so revolutions and bloodshed. That means that we have to assume that we have a capitalist system. The big thing there is that monetary incentives are a very strong incentive in the capitalist system. So if you look at the bottom there, I think to me, one of the big tricks is to figure out how to use capitalism, and in particular, these monetary incentives to get people to do the changes that are better from a carbon or other point of view. Okay. So what can we do? Let's talk about a few other things. This I showed last time. The point I'm trying to make here is if you look at the orange box, electricity generation, we have to replace the natural gas and coal by something else that's cleaner, right, for electricity generation. But on the left-hand side, you look at the energy services and rejected energy. Fossil fuels are so inefficient that most of the energy is rejected through heat. Okay, so if we replace things like vehicles with electrified versions, we're going to have a much more efficient use of the energy. So we don't need to replace all of the energy there. So we don't need to replace the 31 plus 65. We only need to replace a portion of that. Okay, so a lot of people are saying we need 3 or 4 times the amount of energy that we have now. No, we don't. We probably need twice as much electricity as we have now. But I'll leave it at that for now. So the efficiency is a problem with fossil fuels, right? I talked about the internal combustion engines and right. If we talk about heating, so if you're heating with natural gas, you get close to 100% efficiency in the upper 90s anyways. But an air source heat pump will give you 300 or 400% efficiency. It's pumping the energy instead of creating the energy or the heat. So that allows it to get above 100% efficiency, right? So you need a lot less energy. And like, again, Art would tell you, his ground source would give you even more efficiency, right? So generally speaking, I think in every single case that I'm aware of, an electrified solution is more efficient and much more efficient than the fossil fuel equivalent. Okay, so we need to replace that black box at the bottom of the previous screen, not the top part, because that's mostly rejected heat. Okay, so we don't need to triple electricity production. 1.5 to 2 times is probably enough, and this will result in a reduction of energy use per capita. So I know this is something that Dave was interested in, but that's the way we could reduce energy use per capita anyways. So where do all the emissions come from? So the reason I talk so much about energy is because, as you see there, energy is a very large, it's about 3/4 of the emissions. There's other sectors there. What I'd like to point out, though, is that there's a few cases that are interesting there. Aviation is about 2%, shipping around 2% also. Steel, iron and steel, 7.2%. Cement, it shows 3% there, but I believe that only indicates part of it. There's some energy elsewhere that's also part of that, because the cement industry themselves, they'll talk about 7 to 8%, about the same as iron and steel. So there's a lot of sources of energy, and we could go in detail through all the sources, but I'll talk about some of them and what's possible to do there. So heating, I've already touched on that, right? Heat pumps, they could be used not only to heat space but also water. Okay, and heat pumps are feasible up to about 200 degrees Celsius. So that's interesting, because beyond water and space, you could do other stuff with this heat. So a lot of industrial processes require heat. If you look at the graph on the right-hand side, it shows you the essentially gives you an idea of what percentage of industrial production requires a given temperature, and you can see that about half, a bit more than half actually, of what we need for industrial purposes can be done just with heat pumps. And if heat pumps aren't enough, then we could use resistive heating, electrical resistive heating, and we already do that with electric arc furnaces, which produce temperatures in the thousands of degrees Celsius, and that's used actually to recycle steel. Okay, so let's go through more again. So transportation, I'll go through each one of these in a bit more detail, but the point I want to make here is on top there, what you're seeing is those are called azipods, and that's what is used to propel cruise ships and other ships these days. So that essentially, the azipod contains an electric motor, and there's a diesel generator in the ship that creates electricity, but it's the azipod that's electrically moving the ship. Okay, so the biggest motors out there are actually, in many cases, they're not diesel, they're electric. and a diesel motor is there to make electricity to power the electric motor. Locomotives are a good example of that, and there's many others out there. So let's start with light duty. So this is the CEO of ExxonMobil. He's saying that every new passenger car sold in the world, not just in the US or advanced economies, will be electric by 2040. Okay, so when you look at this and you think about it from a disinformation point of view, well, if he was telling you something like, in 2040, all cars will still be gas cars, you'd be thinking, oh, that's suspect because that's in his interest that would happen here, right? But if you look at this case here, this goes against his self-interest. So you could be sure that this is likely to be a true statement. Okay. So that's one way of finding disinformation. If you follow the money and the money isn't good for him, then it's probably a true statement. Okay. So actually, I'll just rest my case on that and and go on to the next category. So if you look at medium and heavy duty transport, there's already lots of electrification happening there. We have the Tesla Semi there that I'll talk a bit more about later. But I did a survey last fall for another presentation I did, and I looked at every single OEM that I could find in North America and Europe. Every single one of them except Western Star, which are sort of like the rednecks of the truck industry. Everyone had either an EV in market or had announced one that would be available in market soon. Okay, so this is moving quite fast, and if you do the math for the cost of diesel versus electricity, if you're concerned about spending money, electrified solutions rapidly become better. So if you look at ships, ships is a bit more difficult. So the top one there, that's Wolf Island Ferry. It's an electric ferry that contains about 75 vehicles. So that's a solution there for relatively short haul. When you're looking at a long haul, it's a bit different though. So one of the things to note though is that about 30% of long haul shipping is for fossil fuel use, either crude oil or products of fossil fuel. And they actually account for about 40% of emissions because they tend to be heavier ships that ride lower in the water. So they use they overachieve on their use of emissions. If we eliminate fossil fuels from our civilization, we don't need all this shipping anymore, right? So a good portion of the shipping would just disappear if we stop using fossil fuels. There's other solutions for long haul because we're going to have, long haul shipping also. Biofuels are a possibility. There's efficiency measures that could be applied. There's sales. So if you look at the picture on the bottom right hand, that's a concept there. It's not a real picture, but it gives you an idea of what the possibilities are. So sales like that would probably reduce the energy requirements by 30 or 40%. So you get some of that back, right? The other thing that could be done with ships is to use shore power when they're at shore, so or at port. So a lot of actually, ships typically spend a lot of time in port and don't have to be using diesel generators to run the ship while they're there. Cruise ships, similar issue. Shore power could be used. They're starting to do that actually with some cruise ships. And batteries. Batteries are a possibility, but again, if you're doing long-term or long cruises, say from the west of the U.S., California to Hawaii, well, you're probably going to have to use some liquid fuel of some sort. Okay. If we go on to trains, if you look at outside of North America, most of the trains are electrified already, whether it's passenger trains or goods carrying trains. There's a lot of electrification, and where it's not electrified, it's quite feasible to continue that. In North America, a bit different. We could electrify our lines, but other solutions exist. So if we use battery electric, remember that I said there's diesel electric locomotives. There's a diesel engine that just produces electricity. Well, we could put a battery instead and keep the rest of the stuff that's in the locomotive. So there are relatively simple paths to use battery electric. The weight of the batteries is not a huge issue with trains because of the efficiency of rail transportation. And if you think about it, you could have rail cars that are batteries that you would swap out as the locomotive would do its would go along its way, right? So other thing to note is that you would recoup some electricity going downhill, and that's very similar to what we get in cars. And I'll Go on to aviation. So if you look at short and medium haul aviation, the picture on the left top, that's a concept. That's a plane that is designed to fly 800 kilometers with about 100 and some passengers. So that's becoming quite interesting. The picture on the top right, and that's an actual picture of Alice, which is a concept plane that they've started testing. I think it's about 12 passengers, that plane. The bottom right, that's actually in production right now. Pipistrel has an electric trainer that they're selling to flight schools. Flight schools, one of their biggest costs is fuel. If they could use electricity instead, they save a lot of money, right? So the biggest issue right now with flight is that we need batteries with higher power density by weight. The good news there is that there's already some batteries that are in the 700 range that are commercially available in limited quantities at this time, but there are some available, and that is improving over time. So we will be able to see things, distances improve and size of planes and all that improve. Here, long haul is a big problem. So hydrogen is not the answer. I just want to cover that for a second. So if you look at the gravimetric density, it's true that you get 4 times more energy out of a liter of a kilogram of hydrogen. So that's a good thing. But however, that means that your fuel will weigh less. However, you need to put that into a compressed tank of some sort, and the tanks happen to be heavy. So you're probably not going to gain much in terms of weight. If you look at the volumetric density where the problem really lies, jet fuel is 4 times more energy dense by volume than hydrogen. So that means that for a typical 747, like you see there from British Airways, that would carry 250,000 liters. Think about that. You're doing one long haul flight, 250,000 liters gets burned. To do the same thing with hydrogen, have the same amount of energy, you would need to have 1,000,000 liters. Okay, so think about that, and of course it's a Photoshop thing on top there, but it's to illustrate the point that there isn't space and to put that in a conventional airliner, and again, the weight of the containers would be a real issue, right? So what we're looking at doing is using synthetic aviation fuel, referred to as SAF, and a reminder that aviation is only 2%. So, although we can't fix all of aviation, it's a relatively small percentage. So we shouldn't focus on the things that are harder. We should focus on what is doable in shorter term. So I'm going to try to speed up because I always have too much material. So anyways, one of the things I heard a lot is that refineries will produce gasoline and diesel, whatever, regardless of demand. So as long as we have, demand for plastics or whatever, we're going to be producing this other stuff. So why not burn it, right? So this is really a myth. If you think about it logically a bit, it'd be quite a coincidence that refineries are producing exactly what we happen to need now, right? So this is incorrect. What they're you may have seen that refineries will switch from summer to winter production, so they'll switch from gasoline for cars to home heating fuel. So there's flexibility in there to change the proportion of what you make with a barrel of crude oil. So if you look at the refineries, they fraction what's in a barrel of crude oil and get some components there that they could use like that. They just fraction it through distillation. But also they do things like cracking. So as it says there, cracking takes complex organic molecules, so big organic molecules, and breaks them up into smaller molecules that you could actually use for some whatever purpose. So let's talk about some chemistry here a bit, and I'm going to try to do this fairly fast. But organic chemistry, right? When you talk about organic chemistry, it's chemistry of the carbon atoms or carbon compounds. Okay, so about half of chemistry is organic chemistry. Inorganic chemistry is all the other stuff. So if you look at the different molecules on the side there, so you'll see that there's lots of variety. As a molecule gets bigger, the melting point and boiling point gets higher and all that. So all of these have different properties, and and different uses, right? So these could be combined in many ways. Okay, so there's many things you could do with various industrial applications. Aside from energy, you could make polymers, adhesives, all sorts of other stuff. So this, I didn't fact check this number here, but somewhere around 20%, somewhere around 40 chemicals are the precursors that are used for everything else that's used industrially in the organic chemistry side, so petrochemicals and that kind of thing. And most of these are available, if not all of these are available from non-fossil sources. Okay, so you could use biosources which contain carbon to end up with the same chemicals. So keep in mind here, the petrochemicals, you're not intending to burn the product, so it's a bit of a different issue. Okay. Here, I just want to show ethylene just for a second. That ethylene is in the middle there. We could use, we could synthesize that with methane, which we could get from renewable sources. And then if you look there, I'll let you have fun and look at this stuff. But on the right-hand top side, that's ethylene glycol. That's that's antifreeze, right? There's ethyl benzene that then becomes styrene. Styrene is, think about that, polystyrene, right? On the left-hand side, you've got polyethylene. So again, plastics, right? And vinyl chloride. So vinyl chloride, right? Vinyl is another form of plastic. So there's a lot of things we could do with the precursor chemicals to transform them into something else, right? The one thing to note here, though, is that all the reactions, well, most of them actually, some are exothermic, but most of them require some heat to be applied or some energy to be applied. So that means there's cost, and also there's cost because you need the equipment to be able to do this. So there's no free lunch. So some of these things, the reason we use petrochemicals today is because it's the cheapest way of doing what we're doing. It's not because it's the only source of precursor chemicals. So I'll skip over this one. You can have some fun and look at that later, but it's a diagram of what a refinery would do with the cracking process. So organic chemistry is really fascinating, and it's amazing what you could do with one organic compound to transform it into another compound. The combinations are literally almost endless. Okay, so that's petrochemicals. Let's talk about steel. So if you look at conventional steel smelting, what happens is that coke, which is a refined version of coal, which is almost pure carbon, is mixed with the iron ore. Okay, and the iron ore is put FeX there. X represents a variable, right? Oxygen. Y is a variable. There are different compounds in the iron ore that are I can't remember the name, but they're oxidized versions of steel. Sorry, not of steel, of iron. Okay, so what we're doing in a conventional smelter is we're taking now those oxidized compounds and we're adding carbon, and the chemical reaction is that you get pure iron and you get CO2, lots of CO2, lots of emissions, right? The coke that's put in there has got three purposes. Purpose number one is to heat the reagent. So a lot of the coke is burned to heat it. Lots of emissions. The chemical reduction, which is the chemical thing that I'm showing there, that results in CO2 emissions also. And there is some carbon that's left in there that needs to be in there because iron is not particularly useful as a metal directly. Where it becomes useful is if you make it into steel. You need a bit of carbon there. Typically up to 2% content is steel, is carbon in steel. The net result, though, 1.9 tons of CO2 per ton of steel produced. That's a lot of emissions, and it represents about 7 to 8% of global emissions. So if we could tackle that, it's going to be super useful for us. So look at what's referred to as green steel. There's a few different things that could be done there. So you could use hydrogen. So, remember I said hydrogen would play a role elsewhere. So hydrogen could be used to run a chemical reaction that will strip the oxygen from the oxidized iron ore. Okay, so you see there the equation. So you're adding hydrogen, and what you get is iron plus water, right? Water is is much less of an issue than CO2, right? One of the nice things here is you could reuse the existing infrastructure to a large degree. You could use existing blast furnaces to do this. Okay. The other thing, oh yeah, here just mentioning that steel, so you need a bit of carbon. Remember I said before that electricity is often the best choice. Well, it turns out that there are companies, Boston Metal here in particular, they're working on something called thermo electrolysis. So they're using electricity and heat to purify the iron ore, and it's more efficient and should be less costly over time than using hydrogen. There's another company working on something called low temperature electrolysis. So a temperature of 60 to 150 degrees Celsius. And recall earlier, heat pumps work up to 200 degrees Celsius. So they could be using heat pumps to heat the material and then electricity to actually process it. Okay. So that's steel. So we could, we have pathways to get rid of emissions in steel, or most of the emissions in steel anyways. So if you go to cement now, cement, I know the diagram said about 3, but everywhere else I see 7 to 8, and I think that's because of how the data is aggregated in that diagram. So cement is about 10% of concrete. Okay. And what generates the emissions is the production of cement. The rest, the 90%, is aggregates and all that are added in there to make a bigger mass. So if you look on the right-hand side, more or less shows what the process is. You take limestone, and essentially you run it through some kilns at very high temperatures, and what you get is at the bottom there, it shows that you get essentially cement plus a bunch of CO2. So you get lots of CO2 emissions, and the emissions, you get them from 2 different places. You get them from the heating, because they use fossil fuels to heat the limestone and the other raw materials, but you also get some from the chemical reaction. The heat, we could use electricity and get rid of the emissions that way. That's a possible path, but the chemical reaction is a much bigger issue. So the result is you get about 1 ton of CO2 emissions by ton of concrete, not ton of cement, but ton of concrete. So now there's some companies that are looking at the chemical reaction part, and it's very hard to actually get rid of the emission itself. But what you could do, though, is if you think about it, you've got limestone and you're processing it to make cement. Limestone is a rock, right? So maybe if we reverse that process, we could capture the carbon and we could get a rock back, and maybe that's what we need to build stuff. So essentially, that's a bit of an oversimplification, but you've got a bunch of companies that are working on processes to reabsorb some of the CO2. This works really well in a plant. So if you're making bricks and stuff like that, or prefabricated panels in a plant environment, it's relatively easy because you could control all the environment. This is much more difficult if you're doing ready-mix concrete, which is a big proportion. But anyways, there are a bunch of companies that are working on ways to decarbonize cement. Okay. So if you look at emissions from a different perspective, and you look at the product life cycle, so you probably heard that we talk about scope 1, 2, and 3 emissions, and scope 1 are the ones that you have under your control, where you make the decision of what is used and which process and all that, and whether it results in greenhouse gases or not. Right. The other 2 scopes are out of your direct control. But what I want to do here is I want to go and talk about a specific case. So if you look at a Tesla vehicle, right? So how can we decarbonize a Tesla vehicle and the overall life cycle emissions from a Tesla vehicle? If you look on the right-hand side, that yellow, so that's an internal combustion engine. The yellow is the combustion of gas or diesel, and there's very little things you could do to get better efficiency there, right? We've rung all efficiencies that we could probably possibly get out of internal combustion engines. So there's not much we could do there. If you look at the blue portion, that's the manufacturing of the vehicle. There's a lot we could do there, and we'll talk about that in the next slide. On the 2 first columns, those are battery electric, 2 cases of battery electric. The yellow is the electricity you use to actually power the car. Art will again, Art will tell you that he's using his solar panels, so there's not very many emissions coming out of that. Okay, so and we could talk about the embedded emissions in the panel and all that at some point. But anyways, bottom line is you could reduce that those orange boxes to next to nothing, and the two greens, that's the battery, the assembly of the batteries, and the minerals for the batteries, and those there's also ways to reduce those. So if you look at that, there's really four sources that we saw in the previous slide of emissions. Okay, so the vehicle manufacturing, if you look at it, well, the first Tesla I got was almost all aluminum, and the aluminum was probably processed through an electrical process with clean energy from places like BC. So there's very little emissions there, right? Steel, like I explained, we could use either electricity or hydrogen to reduce emissions there. Excuse me. The plant itself could be using electricity to heat and water and space. We could use green electricity instead of fossil fuel-based electricity. We could use electric trucks. The mining could be electrified. I mentioned paint here because it's an interesting one. Volkswagen, when they tried to get rid of Scope 1 emissions for their plant where they make EVs in Germany, the paint shop was the biggest problem they had. Okay, so the emissions come from cooking, so that's heating the air to cook the paint, which is part of the process of painting a vehicle. And there's also volatile organic compounds that are released. Those are typically captured, but let's put that aside for now. So to build the building, right? So embedded emissions in a building, you could use green steel, you could use green concrete. One thing I don't mention here is you could use mass timber, which actually sequesters some carbon. Glass, there's a lot of work in Europe to decarbonize the production of glass. Right now, they use lots of natural gas to heat the raw material to make glass. And so a lot of scope there to get rid of emissions. If you look at the assembly, there's you could use green electricity, and the other is you need to charge and discharge the batteries after you manufacture them. They have a term for it. I don't remember what it is, but more or less to condition the batteries before you actually ship them off. And there's adhesives and fillers and a bunch of other stuff there that it can be decarbonized to some degree or other. Same with the battery minerals, right? We could source them locally. We'll see an example in the next slide to avoid shipping by sea, which is difficult to abate. And electric mining is becoming a more common thing. So so bottom line is for battery minerals, we could take a lot of the carbon out of that supply chain and reduce the carbon that you account for when you look at the vehicle, right? And the electricity, again, if you talk to Art, you'll get an example of someone who's having very low. Oops, I forgot to put these on here. If you talk to Art, you'll have examples of very low carbon electricity. Okay. So if we go a bit further and look at Tesla in North America, and I don't want to talk about Tesla because they're better than others. It's just because I'm more familiar with their operations in North America. And what they have is they have a plant in Nevada that makes batteries and powertrains, and they assumedly, like they said this in the past, that they would use only green energy to power that plant, right? So they've decarbonized the electricity to power that plant. Fremont and Austin, those are the two assembly plants they have in the US. They're supposed to be using green energy there too, so they've decarbonized that. They could use electric trucks to transport the batteries from Nevada. They're not doing that right now, but as you saw earlier, the Tesla Semi, they should be starting using Tesla Semis soon to transport the batteries from Nevada to Fremont and to Austin. And of course, the same with all the other raw materials that are being used to make these vehicles, right? Talked about paint again. You could use electricity instead of natural gas to heat, and the VOCs could be captured. If you look at raw material, so Tesla is looking at sourcing some lithium from Nevada, actually, which is not too far from where they want to process it in Corpus Christi in Texas. So so that would mean that they could use electric trucks, use electric heating and all that to do that. So decarbonize that part of it. And again, electric mining could be used, and it's already used for things like nickel. So if you look in Sudbury, what they're doing with underground mining, it's largely electrified already for a bunch of reasons. so there's a lot of scope to decarbonize there, right? So every part of the supply chain, there are things that could be decarbonized. Some of them are easier than others, but there's some scope to decarbonize, right? You may remember from the last presentation that the global share of electricity for fossil fuels is dropping and solar and wind is going up. So the grids are getting cleaner. And over time, we should see grids that are largely free of fossil fuels. So the electricity you see here, the orange you see here, will will have less and less emissions over time. So if you look at these this diagram on the right, the yellow, like I said earlier, there's not much we could do about that, but because that's a combustion of the gas or diesel that you have in the ICE vehicle. The blue, though, we've just seen that there's a lot of stuff we could get rid of, right? We could use clean electricity, we could have decarbonized processes, decarbonized supply chains, so we could make that quite a bit smaller. On the left-hand side, the orange, like I said earlier, we could bring that to a very small amount. The two green portions, there's also some room to squeeze a lot of carbon out of that. Okay, so if you're looking at what you see in the yellow there, that's about, I believe it's 36, I don't see my notes there, but about 36 tons over 200,000 kilometer lifetime of this vehicle would be emissions from a gas vehicle, right? But if you look at the electric version and you decarbonize the supply chain and the production of electricity, you get to a few tons fairly rapidly. Okay, so it's possible to get rid of a lot of carbon in supply chains, and that will that will allow us to rapidly decarbonize a bunch of things and reduce the emissions. So what does it mean for fossil fuels? I'm going to try to go a bit faster here because I'm already running pretty late. Uh, so it means a rapid reduction in the amount of fossil fuels that are going to be used. Won't belabor the point
Yeah,
here.
I was just about to give you a bit of a reminder, Art.
Yeah,
So you're bringing things to a close. Thank you.
yeah, yeah. I'll try to speed it up a bit so we could get to questions. So, anyways, so I'll skip on this one for a second.
Ray.
So, yeah, go ahead.
Sorry, I called you Art. I meant
Yeah, yeah.
Ray.
No worries, no worries.
Okay.
So if you look at it from a GHG emissions point of view, the curves you're seeing there are curves from these are forecasts from the IEA, and like I said before, the IEA tends to underestimate things. So my reading of it is the emissions are gonna fall at the rate that we see in the green there, the NZE. Here we have methane also. So methane and CO2 are the biggest contributors, right? So we're going to see a large decrease in emissions. Okay, so what does that mean from a point of view of GHG concentrations? So GHG concentrations is what causes global warming, essentially, right? It's not what you put today; it's what's been accumulated over time that's an issue. So the concentrations will continue to rise for some time because it'll take some time before we reduce emissions enough that so it lags emissions, and it's going to take some time before we reduce emissions enough that the natural processes will be able to absorb what we're adding to the atmosphere. Okay, so there are some natural absorption mechanism. Weathering is one of them, but oceans also could absorb somewhere between 25 to 30% of the CO2 that we emit, right? So we don't need to drop to net zero to see an inclination in the curve. So if you look on the right hand side, the blue curve, light blue curve, you see that by 2050, even though we get to in the scenarios that they have there, we get to net zero by 2050. We're already a bit on a downward trend a decade or so before that. Okay, so what we should see is a topping up or a peak of concentrations and then a drop down from there. So why are we talking about all these different sources? It's because these are the sources that are causing all these greenhouse gases, right? So again, if you look at this diagram, we have passed to some of them I didn't discuss, right? Didn't discuss agriculture and waste, but most of these sources we have passed to get there to reduce the greenhouse gases quite fast. Um, proof of this? Well, this is something I showed last time. So China is actually set to peak their emissions in 2023 or 2024. That's 7 years ahead of what they had promised in Paris. Okay, so things are moving a lot faster than we were expecting, and a lot faster than planning is showing them. So China in particular is exceeding by a large degree their objectives, right? So this is the last slide. So these are the same books that I showed at the previous presentation. One thing I'll tell you is Not the End of the World from Hannah Ritchie. Super book to read. A lot of what I cover here, she covers in the book. She covers a few other things that I don't. But it's a really good book if you want to have an understanding of where we are and what the trends are, because she uses real historical data from our world in data, right? And so it's real data, reliable data that shows trends, and she uses those trends to show us what the future might look like. Okay, so on that note, I'd like to pass it back to Nigel.
Thank you very much, Raymond. It's a very substantial discussion on what we need to think about in our choice of energy. And let's go to the chat. There's several comments. One, David Doherty, you had, I guess it's more of a comment, or is it a question on the ability of oceans to absorb greenhouse gases?
Okay, so that was actually a discussion I was having with one of our other members about how much of what we emit goes into the oceans. And what I was recounting to people before the session started was that I somewhere had seen about half, and the response was that it's actually about a quarter. I was able to verify that the U.S. government through NOAA and satellites has set it at about 31%. It's resulting in the acidification of the oceans, of course, and it will be affected as the oceans warm, because they'll actually absorb less gas as things warm. So that was all that was about.
Yeah, I do want to comment on that a bit. I read a couple of books about the ocean and how the currents work and all that, right? So some of the currents that are out there are sequestering water in the deep ocean for literally thousands of years in some cases, right? So I think there's still a lot of capacity to add CO2 into the ocean, but the problem we have, like you said, is acidification, right? So acidification is a real issue with anything that's trying to make a shell in the ocean, right? So it'd be best if we could reduce the acidification as much as we can.
The other thing to remember in this is that all along the oceans have in fact been sequestering some of this carbon. It certainly hasn't stopped the atmosphere from increasing in temperature.
Okay, yeah, thank you. Okay, thank you. Now, Brian Kelly, I'm not sure if he is here, but perhaps it was sort of a question that occurred to me. It was more of a comment. He said, well, I guess earlier in the discussion, how can Toyota get it so wrong? And I think he's referring to, which is kind of an interesting observation. And as I think the comment was something to the effect that he thinks EVs will top out at about 30% of sales.
Yeah.
Now, so he's more on the pessimistic side. What do you think his projections might be based on? Or
so the Toyota situation is a bit complicated, and Toyota situation actually is not just Toyota, it's all the Japanese manufacturers. What happened at one point 20 or so years ago is the Japanese government for reasons that are peculiar to Japan, right? Japan's a very small island and all that. They thought that hydrogen would be the future for transportation and energy uses. That wasn't not unreasonable at that time because we didn't have batteries that would allow us to electrify stuff. And there's a lot of things that, hydrogen looked like it was, although it'd be more expensive than what we're doing right now, it would be the best solution that we would have that would allow us to decarbonize. So Japan essentially and the car manufacturers went full bore trying to make hydrogen a thing for the transportation system. And if you know anything about the Japanese culture, there's something about not losing faith, like saving face, right? You don't want to be changing a decision because that's admitting that you made a wrong decision before, right? So what we've seen is all the Japanese manufacturers have been pushing this hydrogen thing very hard, but now we're seeing some of them starting to invest in EVs. We'll talk about all of them, but the problem with Toyota is at this point in time, if you're Toyota, you've got you're way behind the ball in terms of electrifying your fleet. Okay, although they did have an advantage when they came out with the Prius about 20 years ago, right? But they didn't seize that as an advantage. So right now they're way behind everybody else, and they're trying to convince people that their product is still worthwhile, right? So if you look at this 30% share, if you look at the adoption of technology, that's just not the way it happens. People, things don't stay at a partial level. The best technology and usually the cheapest technology is the one that wins over, and electric is certainly the cheapest and best technology, especially as you move into the future, right? So Toyota, very bad situation. If you look at people in the EV world, none of us are very impressed with Toyota. And I could go on about it, but and they're actually, to me, they're misinforming the public because they're selling things like self-charging EVs and that kind of thing. So to me, it's misleading the public, and it's nice to say the plug-in hybrid will reduce your consumption of fuel and result in less GHGs. But it's not less that we need. We need to get rid of all the GHGs. So you can't do that with a plug-in hybrid. Okay.
Okay, thank you. Art, you had a question and a comment, question regarding the use of hydrolysis with excess solar.
Yeah, I want to make a comment which I find rather interesting. In Western Australia, there's an iron ore mine that is about on quite a slope going down to the coast, 220 kilometers, if I remember the distance correctly, where they have a full lithium-ion battery train that once it's full of ore, it's doing regenerative braking going down to the coast, where they offload then, and the batteries are charged up enough where they can haul the empty cars back up to the top and repeat it again. I thought that was quite creative in terms of using potential energy to capture some energy. Anyway, the question really comes down to if there is, existing markets, as we know there are, for hydrogen. And again, it reminds me of an Australian example, where out beyond the end of the grid, as it's reaching into the outback, where they set up lots of solar energy to generate electricity to run the operations in the mine. But they overbuild. They make it bigger than necessary, for contingency and what have you. But then they also use the excess energy for hydrolysis and to make both hydrogen and oxygen, which they then can sell on existing markets. And their plan is, of course, to use that hydrogen to, as it were, truck further into the outback for the next mine that's deeper in. And I look at all this and I say, there's got to be some economics here that says that even this doesn't make sense. I mean, overproducing, intentionally overproducing, from solar to use the excess that you're not using, of course, to make hydrogen. Do you have any comment on that? Have you run into this before?
Yeah, actually, several times. If you listen to Tony Seba, what he's proposing is that we overbuild renewables so that we have a higher baseline of production, so that when we get these windless days and all that, that we have some buffer to be able to last longer, right? And don't require so much storage. So there's a lot of people talking about overbuilding, building 2 or 3 times the amount of renewables that we need when they're running full bore. And what they're talking about is that, okay, there'll be a lot of excess energy then at some times. So what do we do with this excess electricity? And they're saying, well, one of the great uses would be to electrolyze water to make hydrogen. The problem I see there, I think conceptually it's a great idea. But the problem I see though is that so I've attended. There's an organization based out of Germany. It's called Mission Hydrogen, and they have regular seminars and they've had conferences that I've attended also, because I've tried to understand, where are they coming from? How can you possibly make this hydrogen stuff work? And one of the seminars that I attended, they looked at the cost of setting up electrolyzer plants to do green hydrogen. Okay, and if I remember the numbers correctly there, and don't remember everything, but the cost of capital for the equipment to make hydrogen, forget about electricity costs, the cost of capital alone was somewhere around $10 a kilogram. That's assuming you're running these electrolyzers as much as you can. Okay, so you're running them 100% of the time except maintenance, right? So you're really pushing them. You're not just running them when you have excess cheap electricity. You're running them all the time, and the capital cost alone is very high. Now, that is likely going to go down over time as technology improves and all that. And actually, Bloomberg New Energy Finance, they're forecasting that by somewhere around 2030, that green hydrogen will be at cost parity with the one made from methane. So there may be a route to get there, but there's real issues with the structural cost of the plant and the electricity you need to be able to do that, right?
Good answer. Thank you.
Thank you. Now, Raymond, I don't see a question next in line, but I have one regarding battery research. I've read quite recently, there was a big article, actually, I think it was in the Globe this weekend, about battery research, and some of it being done in Canada, particularly at Dalhousie University. But there is the possibility of using new elements in combination with in or without in combination with lithium, say sodium or sulfur. My question is, I mean, I know that sodium is an incredibly reactive compound. Are there safety considerations as we increase sort of the energy density in a battery? Are there some sort of ultimate limits?
Well, that's an interesting question. There are physical limits, because if you think about what's happening in lithium-ion battery or sodium-ion battery and all that, you're taking electrons and moving them around, and there's only so many electrons that you could be moving around. Okay, so there's a bunch of factors that'll affect the energy density, but ultimately there's a maximum number of electrons that you could actually leverage to get what you want out of the battery, right? So if you look at sodium, yes, it is. So pure sodium is quite reactive, but pure lithium is also very reactive, right? That's part of the reason why they're in the same place in the same column in the periodic table, right?
Yeah.
But also that makes them good materials for batteries.
Mhm.
So you know this the safety the safety issues we've had with batteries have been mostly with the older batteries. So lithium ion, nickel, manganese, cobalt chemistries, where the electrolyte actually was flammable in contact with oxygen. So you know, if you breach the canister, the thing would start burning, and sometimes burning really hot very fast, right? So there were some fires with batteries in the past that were caused by that. The newer batteries we're looking at right now that are becoming more common. So my new car that I just got, it's got LFP, lithium iron phosphate batteries. So there's no nickel, no cobalt, which are problematic in terms of supply and all that, right? But also the electrolyte is not flammable. So that means if you breach the container, it won't spontaneously combust. And actually, there's interesting videos on YouTube about this. You could drive a nail through those batteries and they will still function. Okay, that's not true of some of the older chemistries. And so with sodium, sodium is there's all sorts of constraints that are different with sodium than they are with lithium. Sodium could have more, it could lose more electrons and all that, so it could theoretically store more energy. But the problem with sodium is it's a bigger atom, and when you're charging and discharging the battery, it tends to inflate and deflate, like right, and that degrades the battery. Now, there's some researchers that have found ways around that. so, so there are actually sodium ion batteries commercially available, and there are quite a few cars in China that are running with sodium ion batteries. So we're going to see those, show up more and more commonly here in North America over time. Why? Because sodium is much cheaper than lithium, right? So if you could have a battery that's going to give you is going to cost less per kilowatt hour of charge, that's a big advantage. Now the weight could be a problem, right? Because the energy density is not necessarily as high. Theoretically, sodium should be able to get much higher energy densities than lithium batteries, but because of those limitations and because of having to have a structure of the battery, if I could put it that way, that takes that into account. We haven't got the same amount of energy density yet in the sodium ion batteries, but there is a chance that eventually, as research progresses,
Mhm.
that
Mhm.
we'll get into sodium batteries that will be better than lithium ion batteries in terms of energy density from a weight and volume perspective, right? So research is moving quite fast, and we're seeing a lot of stuff coming out, and so there's a lot of progress that we're going to see with batteries over the next number of years. This a result of what we've been the amount of money that's been invested in research
Yeah.
over the last decade or two.
Yeah. Thank you. Thank you. Art is going to ask you a question on V2G, and next Susha Man has a question after that. Go ahead, Art.
Yeah, I know that in the Hydro Ottawa area that there is a pilot of some type going on vehicle to grid, and I understand you're part of that. And I'm outside the area and I'm not part of that. And could you just bring us up to speed as to what the objectives are and what really is holding back V2G taking off big time, throughout the world?
Okay, that's lots to unpack there. So the pilot that I'm on with Hydro Ottawa, which is we're really in the alpha version of the software they're using. It's a demand management pilot, right? So they could control when our cars get charged, but they're not getting energy back out of the car, right? So I'm sure you know that with Teslas, it avoids a warranty if you try to do that anyways, and you'd have to jerry rig something to be able to make that happen, right? It's possible to do it, but it technically voids of warranty, right? What we're seeing though is if you look at the F-150 Lightning, it's designed to be able to feed the house and support the whole house for like 3 days. So we're seeing vehicles coming out that support that type of functionality from the get-go, right? And what we have seen also is manufacturers, including Tesla and Volvo in particular, and I think GM and Ford have said the same thing, and I'm not sure though, that they will all support getting energy out of the battery and feeding it back to the house or the grid. Okay, so I've done a presentation on that before. You probably remember. I think there's a lot of potential there because these batteries are very big, right? So the batteries that I have in my cars, they're about the size of 5 of your power walls, right? And the battery's sitting there. And if you listen to Jeffrey Dahm from Dalhousie that Nigel referred to a bit earlier, he's saying the batteries we have today are good enough for millions of miles. So using the batteries to feed the grid when we have peaks should not cause a significant issue with the batteries. So, we're paying for the batteries anyways. We have them. Why not use them for this extra purpose, right? Right now, there's two things that are making this slower. There have been some pilots though with Nissan Leafs of all things, but let's leave that aside. Most cars don't support that functionality, and also the charging stations are available right now. Most of them don't support the functionality either, right? That being said, lots of research, lots of movement there, and I expect that's going to be a very significant thing in the next 5 or 10 years.
Okay, good. Thank you.
Okay, Susha Man, you have a question. Please go ahead regarding non-limited.
So Raymond, I'm trying to understand if the battery technology in North American EV, do we have non-lithium batteries now commercially available? And the other question I had, I just put it with, is, can I get by the end of this year something like 40,000 Canadian for equivalent to Tesla's Model 3 car?
Okay, let's talk about the sodium or other chemistries. Right now, the only place I'm aware where there's commercially sold sodium batteries is they're using them in some cars in China. And actually, what they're doing is they are replacing some of the modules with, so they're taking some of the lithium ion out and putting sodium ion in. Sodium ion have some pros and cons that are different from lithium ion. So they're using a mix to get the best of both worlds, if you will. Okay. So if you were to buy those batteries, they're probably available. They would come from China. I'm not aware of anybody who manufactures any sodium batteries in North America, but I don't know what everybody's doing, right? But I'm not aware of any manufacturing happening right now. Now, one of the things to know about sodium ion batteries is the production process to make sodium ion is essentially very similar to the lithium ion batteries that we have today. So, it should be easy for an existing battery production line to be converted to sodium ion, right? So current battery plants that are being built today, they should be able to do a sodium ion also in the future. Okay. Now, to your question about the cost of the car, right now, if you look on I think our website is down to the EVCO website. It was down earlier today, anyways. We have a buyer's guide there that has all the vehicles that are available in Canada. There are a few that are around $40,000 that are eligible for $5,000 government rebates, right? Going from memory here, the Kona, Hyundai Kona, and the its Kia equivalent, De Niro. There's a few others there. I would stay away from the Leaf because the Leaf is already still available and relatively inexpensive. There's the Bolt that's still available, and I believe they've already stopped production of this version of the Bolt, but it's a relatively inexpensive car too, right? What we're going to see though, going forward, is as the price of batteries is going down, because of competitive forces, the manufacturers will drop the prices accordingly. So we should be seeing some models being introduced over the next couple of years that'll be considerably less expensive than that, that will give us on the order, on the order of 400 kilometers of range. And if I've been driving electric for 10 years, and what I can tell you is 400 kilometers of range is more than enough to travel anywhere in North America without a problem. Okay, so a lot of people think they need 1,000 kilometers or more, but in reality, that's you're paying for a bigger battery than you need, and you're having to lug around that battery, and it's heavy weight, and you're using more energy and all that, right? So the sweet spot is somewhere around 400 kilometers for if you want to use it to travel long distances. Yeah.
Okay, thank you. Yeah, 400 kilometers is fine for me.
Right, it's pretty good, yes. Well, thank you, Susha. So Raymond, I think it's given the time, and we could certainly have lots to discuss for a continued period, but I think it's a good time to bring our presentation and Q&A to a close. And I will turn it over to Ted Manning to thank you and close. Ted?
Raymond, thank you again for your normal, very high quality presentation. Yeah. This time I'd use the term electrifying. But it's really good to get good news in front of this audience, because sometimes it's a bit of a doom and gloom thing when we keep reaffirming for each other how bad it's getting or likely to get. So yes, it's good to have good news. And hopefully we're going to continue that in the next one as well. So again, thank you very much on behalf of KCOR, and we undoubtedly are going to invite you again, because the news keeps changing so fast. I think we have to talk to you regularly. I'll also note that we are, next week, we have a fellow by the name of Brian Check on degrowth, or can we back off from where we are? And I hope you come to see that. It's another one in the we're now booked well into July, I guess, for our upcoming presentations. I would like to also, again, hit the commercial. All of you who have been watching, if you're not a member, please become a member. That's what helps pay for this. That's what helps let us get the help in setting up the website and the Zoom and things of that sort. We also would ask you, if you wish to watch the videos, please, and we need, let me see, I don't seem to have the whole slide on, so I'll have to try and remember it. But we essentially would like you to certainly indicate you do like the YouTube, because that also gets us more attention and perhaps gets more people to look at it. So I will thank you again, thank everyone for coming, and urge you to come again next week and have another interesting presentation. And as we are now concerned, we will shut off the recording, and we can have an open session to talk to each other on anything we like.